Yep, I'll be around. Good morning, everybody. We'll give it another couple of minutes here. Well, there's still a few people that look like they're joining. So we'll give it another 1 or 2 minutes and then we'll start the webinar. Okay, good morning and good afternoon, some of you out there. My name is Mike Jacobs from Abbott Furnace Company, and we're going to talk a little bit about aluminum brazing today. So this webinar is kind of the first in its series where we'll talk about aluminum brazing. It will be a little bit general. We're going to cover a lot of various topics. And from some of the questions that the attendees have submitted prior to the webinar, some of the feedback that we get during the webinar, and then some of the post follow-up we will try to figure out what topics and subjects for future webinars in the aluminum brazing world. So as we go through the webinar today, there is a chat feature and a Q&A function at the bottom. Please feel free to submit questions throughout the webinar, and if they're not answered during the webinar, we will get back to you after the webinar. Hopefully we can answer the question. So please feel free to submit some questions as we move along, and we will get back to you at the end if those are not answered throughout this presentation. So what is the agenda for today? So I am going to touch a little bit on Abbott Furnace. Who are we? What do we do? We'll get into the CAB process, controlled atmosphere brazing process for aluminum brazing. We'll look at some applications. We'll get into the furnace itself and why use a furnace and benefits of using a furnace. And then we'll look at all the various equipment options and an overview that's required for successful aluminum brazing. It's not just the furnace. There's a lot of pieces that have to go together to get a successful brazed part. So a little bit about Abbott Furnace. Last year we celebrated our 40th year in existence. We are located in central Pennsylvania. We have about 900 furnaces, over 900 furnaces operating now in a whole variety of industries and a whole realm of different heat treating processes. We have about 80 employees right now to date. And we have several of the furnaces that are out there, so we have a lot of experience. And I'm going to get into some of the different heat treating applications and processes that we do. Part of the process at Abbott Furnace is we go back and we look at our past projects to try to gain information on what has worked, what doesn't work, and build upon the successes that we have. We have a lot of options out there, from continuous mesh belts, pusher furnaces, muffle furnaces, tube furnaces. We can do electric or gas heating, do a variety of different atmospheres for the different processes, and the temperatures we can have familiar with are up to 3,100 degrees Fahrenheit or 1,700 degrees Celsius. Started off as Abbott Control Systems before building our furnaces. We do use any PLC brands available, Siemens and Allen Bradley, among others. We do try to incorporate all of our manufacturing into under the Abbott umbrella. So we are actually doing our own control panels and programming here in the factory. One of the things that Abbott believes very heavily on is an informed customer is a better customer. So you will see from our website, from our LinkedIn activity, and other things that you're going to see, we do a lot of customer training through the variety of different furnace types and processes. We do a lot of technical training specific for companies. We do have annual brazing symposiums in both the USA and Mexico, and I'll have some further slides or further information coming up on both of those. Just a whole variety of information that we do put out there to help you in your processes and your experiences. As far as symposiums, we had one last year in the US as well as one in Mexico in August of 2024. We do have another one planned for May of 2025 in Niagara Falls. It's going to be a continuous furnace brazing symposium. So if you are interested, please take a look at the website or the LinkedIn profile that we have. I will have a QR code at the end that you can scan and follow Abbott on LinkedIn, where we do keep very updated on our activity as far as trade shows, symposiums, webinars, things like that. Again, just a screenshot from our website. We do a lot of different, have a lot of information on there. We get a lot of requests on the website for various brochures and ebooks, especially our technical papers and troubleshooting guides. If people are having trouble with something, they can go in, they request a troubleshooting guide, and we do turn those around. It's quite a busy, active part of our website. As far as the various furnaces and processes that Abbott handles, we're well known for our sintering furnaces, being located in a very large population of powder metal customers, a variety of brazing applications, debinding furnaces for the 3D printing and additive market, of course, annealing, heat treating. We're known for our continuous belts, but we also do a lot of roller hearth type furnaces, pressure furnaces, lab furnaces. As you see in the photo there, it's molded pulp drying ovens for items such as egg cartons to dry that into shape. Also steam treating, carbon felt, calcined furnaces, and binder jet furnaces for the additive market. Okay, so enough on about Abbott. Let's talk a little bit about brazing. So brazing, welding, and soldering, all ways to join metals together. The differences for welding, utilizing high heat or pressure to melt parts together. The difference between soldering and brazing, just for definition, is soldering is melting a filler metal into a joint at temperatures under 840 degrees Fahrenheit or 450 C, while brazing is melting a filler metal with flux into a joint at temperatures over 840 degrees C. So that generally is the difference, that 840 degrees from soldering to brazing. Brazing has many options for different materials like copper, stainless steel, aluminum, brass, zinc-coated steel, ceramics. Today we'll focus on aluminum brazing with max temperatures around the 1200 degrees Fahrenheit as a max. There are a lot of different brazing solutions out there. Of course, we're going to focus on atmosphere furnace brazing, but some of the solutions are dip brazing or salt bath brazing. Induction, we're using a process that joins multiple metals together using an electromagnetic field to heat the material without contact or a flame. Torch brazing, using a hot gas torch on or near a joint to weld the pieces together and melt the filler metal alloy being used to fill the gap. Then you also have another option is resistance brazing, joining two metals together by melting a low temperature alloy between them. And of course, the furnace side, there's the vacuum furnace brazing, where the process is being done in a vacuum. The vacuum is pulled and the actual brazing is done in a vacuum chamber. Then you can add a vacuum purge option to an atmosphere furnace by evacuating the air or atmosphere out of the furnace and then backfilling with atmosphere, or in the case of aluminum brazing, nitrogen, with the vacuum purge cab furnace combination. Or you can have the straight cab furnace and controlled atmosphere brazing, which is utilizing nitrogen atmosphere. In cab, just sometimes in the market, you'll see referred to as CAABs, controlled atmosphere aluminum brazing, essentially the same exact thing as cab furnace brazing. So what is the cab process? Controlled atmosphere brazing is using a non-corrosive flux, is the preferred process for manufacturing aluminum heat exchangers of many different designs and shapes for many different industries. We're going to look at some of those industries and some of those applications. The aluminum brazing furnace is the most repeatable and economical means for brazing the components. When you look at the time, temperature, and atmosphere relationships provided by the furnaces, they allow a high volume production of parts. And if you just think of a typical radiator type heat exchanger, there's thousands and thousands of joints per part between the fin and tube joints that we're brazing together in the furnace. The general steps in the cab process are cleaning the parts, fluxing the parts, drying, brazing, and cooling. And due to the unique benefits of the cab process, there's many new applications. So even though the actual process is several decades old, there are still constantly new applications that are coming out, and we're going to go through some of those in some upcoming slides as well. As far as applications, there are many industries that can be used to make these heat exchangers. As you see here, the automotive is traditionally the most popular, what most people have aluminum brazing experience with. But just looking at the automotive side, there are many different parts that can be aluminum brazed together. Radiators, condensers, evaporators, CACs, heater cores. There's a lot of various applications in your automotive car, whether it's a car, truck, bus, whatever it is. One of the new applications that we're seeing a lot of is stemming from the EV market, the electrical vehicle market. And we're going to go through some of those, but basically the battery coolers. There's a lot of heat that needs to be removed, and the systems that do that are typically brazed together, whether it's the actual fluid itself that's brazed together or the mechanism that holds the batteries in place. So there's a lot of new applications that are stemming out of the EV market, and we'll look at a few of those as well coming up. Outside of the automotive applications, there's electronics for such things such as connectors and enclosures because of aluminum's electrical conductivity and heat dissipation. You have construction, could be used for decorative elements and non-structural components in buildings. There are several military applications because it is a lightweight, strong component that can be used. Obviously, aerospace, jet engines, turbine blades, satellites, things, many applications in the appliance industry. Electrical field, brazing is used for fuses, motors, packaging, things like that. HVAC&R, used for rooftop condensers, residential heating and air conditioning systems. It's a very popular and fast-growing market as well, with some different options on ways to braze the components together. Jewelry, another example. So there's lots of examples out there where people can use aluminum brazing as a process. So what is the philosophy of brazing? Essentially, this slide here will break down. You're going to have a heat exchanger with many different components that are individual, different size and shapes, and the brazing will put them all together, and essentially will come out the furnace all as one part. But to make up that heat exchanger, you have many different parts, such as headers that can have different shapes and sizes. You generally have some kind of tube where the fins are connecting to each side, extruded tubes, and some of those can have different shapes of channels inside. And we'll talk about some complexities of these channels, micro channels that create some voids and openings inside. Then you have your fins that are braced together to the tubes. You can have various side supports, end caps, spigots. There's all kind of things that can be added, whether it's brazed or post-braze applications. But you take all of the parts, you put them together in an assembly with some kind of a fixture to hold them in place. And then we start going through the process of cleaning or degreasing, fluxing, drying, brazing, and then any testing where there's pressure test, leak test, and then finally, in some cases, people are painting them for cosmetic appearances. So the philosophy of brazing is a metallurgical bond between the base metal taken by the filler metal. So we're melting the filler metal. It's beginning to flow into the joint that you can see on the right side picture. And if everything is done correct from the fluxing and cleaning and heating, that liquid fillet will flow and fully fill that joint, making it a very hard and contact joint. Part of the process we're going to talk about too is the flux. What's the purpose of flux? How is it applied in this process? But the flux is needed to displace the aluminum oxide. Oxygen is a major enemy of what we're trying to do in the brazing inside of the furnace. So anything we can do to displace the oxygen is very helpful throughout the entire process. The flux also helps to promote filler alloy flow to get that liquid fillet into that joint to fully fill that gap. You have your base metal, and then we have your filler metal. So the process is to heat the filler metal up so it starts to melt and then wick into the base metal to form a very solid and strong joint. Some considerations to look at for brazing are, and these are a lot of the questions as far as designing a furnace too, that we have to look at, is what is the fixture solution? You need some way to hold that entire heat exchanger together and all the parts that we looked at in the past slides. But the fixturing itself is quite complicated, or can be quite complicated. There's a lot of very highly engineered fixtures out there, and some that are very simple and easy, such as just a banding with some predetermined strength that you put on, or tightness level that you clamp it to. But also in some cases, the fixturing can be quite engineered, and in some cases it can create a problem. Even though that the fixture may do a very good job of stabilizing all of the components together, in some cases they're quite heavy, and many times we've seen them even many times higher weight than the actual aluminum heat exchanger itself. I know there's some applications we're looking at now where, just for example, the aluminum may weigh 1 pound, but the fixture may weigh 10 pounds. So when you look at it from a thermal input standpoint, that is a lot of energy, a lot of electric that is required to heat that fixture over and over again. So minimizing the weight and mass is something to certainly consider when you're looking at fixture solutions. But there is a lot of various size and shapes of heat exchangers out there. So your fixture solution is a definite big part of a successful brazing if it's done correctly. Looking at the joint design and strength requirements, are there any pressures that are required? What's the resistance? Are there fatigue issues or problems from a quality standpoint that we have to look at? So the design and strength requirements are going to be based on your end functionality of the heat exchanger. What are the environmental or corrosion concerns? Where is the heat exchanger going? What is the end use? What kind of environment is that heat exchanger going to be placed in? Is it going to be in an automotive car where maybe in the north you have lots of snow and cold weather, ice, salt from the roads, things like that? So what kind of corrosion are you looking at for your automotive side? But then if you look at from an HVAC standpoint, from your stationary air conditioning units, you can have things such as grass clippings, things that may get in there, leaves and other debris. So, the environmental or corrosion concerns is also something to look at when you're selecting your alloys or different materials for your design. There's also the consideration. A lot of manufacturing facilities are using a lot of different materials, doing a lot of various brazing applications. So cross-contamination of aluminum is something to keep an eye on, such as maybe if you're mixing fixtures and things with other brazing processes, for example, copper. Copper tends to uh, adhere to the aluminum if it's in the furnace, and can down the road as it's heated can cause some quality issues there. And then of course 3D printing I put in because it's something that we're seeing more and more of in the heat exchanger design itself. Maybe putting turbulators inside of tubes, different mixers, or complicated internal designs which are intended to create a higher thermal transfer efficiency. So the 3D printing, in some stages it's being developed. We're watching. I don't know how quickly it's going to affect the furnace side, but I know from a drying oven side, there are some complications with some of the internals of the tubes that the turbulators can be creating. As far as auxiliary equipment, there's a lot of things needed prior to the furnace to get your parts through and get a good quality part out of the furnace. Looking at material, part of the material of the part designs. Are you making the tubes yourself, or are you buying them? Same with the fins. Are you making the fins in-house, or buying those? How are you assembling those various components? How are you fixturing them? What kind of cleaning solution are you going to use, whether it's an aqueous washer or a thermal degreaser? What's the fluxing solution? And I'm going to show you a whole variety of different flux options. And then drying and debinding, all is prior to your heat exchanger going into the furnace, where the furnace will actually heat up, melt the cladding, and perform the actual brazing process. So what are the successful steps for aluminum brazing? As far as generally, select the right alloy. You have to have the right clearance in part design. As far as capillary gap, the correct assembly and fixturing, clean part with the right flux and application method and the right amount of flux applied. Then you remove the oxide layer off the part. Remember, oxygen is a major enemy of the process. Drying the heat exchanger prior to going into the furnace, which eliminates oxygen. Heat the metal components up evenly. When it comes to temperature, we want to be plus or minus 5 degrees or 3 degrees C at brazing temperature. And then any kind of post-braze cleaning that's required. As far as the capillary gap, making the perfect joint requires the components to have the right distance between the tube and the fins, or whatever the gap is. Only if that gap is correct can that filler metal spread when turned into a liquid phase via capillary action. A large gap reduces capillary action, and the smaller gaps restrict filler metal flow into the gap. The gap must allow molten flux to be drawn into to clean and dissolve the oxide layer. It must allow the filler metal to be drawn in freely and evenly into that gap, and the gap size will determine the capillary pool. Filler alloy, not in an excessive amount, must be available to fill the joint. And one of the sayings I've seen repeated several times over the year is filler metal can run, but it cannot jump. If the gap is too big, you're simply not going to get a full filled braze joint. As far as the criteria of the furnace, these are the questions that we're going to ask when you come to us looking for a furnace. And these are a little bit basic to start with, but they'll get us in the right direction of your exact process. Is what part are you running? What is the size of the parts? Are these, small 5-inch by 5-inch parts, or are these, 40 by 40-inch type parts that you're looking for? What is the shape of the parts, and what is the material? What's your required production volume? And what's the product mix? Are you running one size part, hundreds of thousands of them at a time? Or do you have a very wide product mix where you're running 5 parts at a time of different sizes? Or maybe you're doing very periodic. You're only running 1 day a week or 2 days a week, something like that. So your required production volume is very important as far as the size, length of the furnace, heating input, things like that. And then from a product mix standpoint, there's also different methods of heating, whether you're going to use a radiation with a static environment where you're doing your brazing, or whether via a wide product mix, if a convection where we're actually mixing up the atmosphere may be a better solution. What kind of production hours are you looking at? Are you a facility that's running 24/7, or you're running 8 hours per day, 5 days a week? What are your required production hours? We'll look at that versus what are your required production volume, and we'll try to size out a furnace or select the right type and size of furnace to meet your requirements. What's the required temperature profile? What's the load orientation? And then some of the process side, what's the cleaning solution, the preferred cleaning solution, the flux application method, drying, debinding, and then what's the required heating method? Whether you're going to use electric heating to heat the muffle, which in turns heat the part, or whether you're going to use propane or natural gas heating. Primarily depends on what's available at your facilities, and it's kind of customized via each customer location and what their past experience is. As far as the typical cab process, I'm going to say this is the typical process. Then I'm going to show you something that changes that, and then we're going to get back in and we're going to detail all of these different steps. But basically, you have your component assembly, your cleaning, fluxing, drying, and then your brazing furnace. But something that changed that a little bit, that typical process or historical process, is some composite brazing sheet. For example, Trillium by Grangus is a material containing a braze liner with optimal amount of flux in the actual material itself, which enables a better brazing with uniform joint formation, improved yields, and minimal post-braze surface residues. It's a much cleaner process. From a component fabrication side, you have your component assembly. And the steps that may not be required that are different from your traditional line is degreasing. You may not need it depending on how you're assembling the parts and what upstream oils and lubricants you might be using. You still need the brazing furnace, but it eliminates the cleaning or degreasing aqueous washing, eliminates the fluxing step, and eliminates the drying step. So there's some capital upfront savings by using this process, as well as shorter footprint internally, and as well as lower atmosphere consumptions, utility consumptions. Because it is a much cleaner process, it has a much lower salt corrosion than typical brazing or historical brazing. It gives a longer life to components such as muffles. Muffles are an item that needs replaced because of the nature of the process. It is a corrosive process, so anytime you can maximize your component life, saves money, extends your production time on your floor. And it is a more environmentally friendly process from the production of HF gas, which is very corrosive and may or may not require the use of an atmosphere scrubber prior to the contaminants going out of the building. An atmosphere scrubber may be used with activated alumina as the actual filtering medium in the filter bed. So back to the more traditional process that the majority of you on this call today are familiar with. Some of you are currently using these processes now, and I know some of you are looking in to these going forward or maybe in your future. But as I've mentioned before, first step is cleaning. 2 ways of cleaning your heat exchanger are traditionally aqueous washing and thermal degreasing. You have various flux application methods, and when we're talking about flux for aluminum brazing, we're talking about KALF4 or potassium fluoroaluminate type fluxes. The application be used as a wet slurry when you're mixing it with water at various concentrations. You can have electrostatic fluxing where you have a negative charge on the part, getting that to adhere to a part. Many benefits and drawbacks to all of these, by the way. You can have paste, paint fluxers, the dip fluxers, or fluxless brazing. So from a flux application standpoint, there are many options that can be used. After the flux application, we have the drying or debinding, depending on whether you're using a wet slurry or a paste. And then we have the furnace itself. Again, many different options and designs, mostly based on the size of your parts and your required throughput. Some typical orientations are continuous radiation furnace, where we're heating a muffle and your parts are inside of a static chamber in a nitrogen environment. We have a continuous combination where you have your radiation portion of the furnace where you're actually brazing is being done. But up front, you can add a convection chamber, which using a high volume of air to increase that heating profile, shorten up the entire profile. And there's many benefits to there as far as mixing parts as well. You could have just a convection furnace without the radiation side where we're putting a high volume of atmosphere through the parts itself. There are indexing furnaces and then many different batch solutions. In the batch solutions, we're generally talking about going in and out of the same door, almost similar to a vacuum furnace where you're going in, opening a door, the parts are going in, all of the different processes are happening and it's coming back out. And we're going to lay a couple of these down on the screen here and walk through some of the steps and the functionality of some of these different processes. But the cab furnace itself includes heating, whether it's gas or electric. In an atmosphere, generally it's nitrogen in the aluminum brazing, and we'll go through some of the requirements of that nitrogen. And then you have your initial cooling still in a nitrogen atmosphere where we're trying to harden that liquid fillet that just became liquid in the brazing chamber. So we're very quickly trying to cool that down to harden that liquid fillet in nitrogen. After that, the process itself is essentially done, but we'll bring the part out of nitrogen and then use your plant air for final cooling for removing fixtures, painting, inspections, things like that. And then a big part of when you're using the Nokolok type of flux is the atmosphere scrubber, which is removing the HF gas, which is produced when mixing the water and the flux going into the furnace. The KALF4 is mixing with the H2O, and that's producing the HF gas that the scrubber is eliminating before it's exhausted out of your building. To look at a layout of a typical cab solution. So at the beginning, we would have a heat exchanger that is clean, and then it would be delivered to a line and go through a wet fluxer. Then it goes through a drying oven to eliminate the oxygen. Then we go in through a purge chamber where we're passing through a curtain chamber into a nitrogen atmosphere. In this model, you can see an atmosphere scrubber placed beside the actual furnace. In this case, we're showing a radiation furnace. So the parts are now in nitrogen. They're going through that furnace length, which is calculated by the number of parts that you're trying to put through and the belt speeds that we've established to meet those required production volumes that you're putting through. After the braze furnace, we go into the atmosphere cooling where the part is a liquid fillet. We're very quickly going to cool that part down to harden that liquid fillet. Then we go back through another curtain chamber out of a nitrogen atmosphere into final cooling in an air atmosphere to cool the parts down closer to plant temperature so you can handle the parts. As far as breaking down the individual steps as we move along through the process is the cleaning. You have the two options, aqueous washer or a thermal degreaser. The purpose of the degreaser is to clean the part, remove the dust, dirt, condensates, grease, lubricants, and oils that have been maybe applied to the fins or tubes on your upstream manufacturing process. Those parts need to be very clean, otherwise the flux will not spread evenly throughout the heat exchanger and into the joint. The filler alloy flow may not fill the joint fully, not giving us a complete brazed joint. And discoloration can occur if there's lubricants and things that are in the furnace contaminating the atmosphere. Part of the thermal degreaser is to elevate to temperatures to flash off the oils or lubricants off of the parts. So the main thing is to get an MSDS sheet of what you're using, find out what that flash point of temperature point is, and then that would become the target of the thermal degreaser. Generally, you're about 500 degrees Fahrenheit or 250 degrees C is a general operating temperature of your thermal degreasers. In some cases, heat recovery systems may be used because we do have various heat producing chambers, such as the brazing chamber, the dry off oven, and the thermal degreaser, all are producing heat. So any kind of heat recovery or reusing any of that already produced heat is helpful on the production side, your cost sides of your utilities. Then you have your cooler that's used to used to reduce the core temperature prior to fluxing. So when the parts come out of the thermal degreaser, they're quite hot. We simply have to cool it down prior to hitting it with flux or water, creating steam. Another method to clean the parts is just a simple aqueous washing machine. Using a water-based cleaning is very efficient. It works very well, using a mixture of water, surfactant, detergents to really serve to elevate the pH is the main goal. A typical solution would have a range of 9 to 12 pH levels. And the aqueous washer does work better, slightly elevated temperatures. But the big problem is, and certainly depends where you are in the world or where you are in the country as far as your local requirements. But there is a problem in some cases with the wastewater disposal issues. So we've seen that before. It can be very costly in some cases. But something to look at if you're considering whether looking at a thermal degreaser or an aqueous washer. But both are quite heavily used in the industry. So now you have a clean part. You're looking to flux the part. So in general, the loading for flux is about 5 grams per square meter, uniformly distributed on all active brazing surfaces. Too much flux, obviously good for flux suppliers, doesn't really hurt the process itself, but excess flux is very corrosive to the fixtures, to the equipment, and will require much more frequent cleaning and maintenance, which is downtime and cost. Too little flux, on the other hand, will give you poor filler metal flow, poor joint formation, bad quality joints, higher reject rates, and inconsistent brazing. As far as the HF gas, the hydrofluoric gas, it is extremely corrosive, which is why we're using an atmosphere scrubber, which is part of the issue with using the wet spray and mixing it with the flux. In some cases, you may require multiple flux concentrations for parts, such as you could be putting a low concentration on your tube to fin joints of maybe 5 to 7%, something like that. And you can be using a higher concentration of flux to the tube to header or the bigger, thicker joints. Put on here 12 to 15%, but it can be much higher. I think in a recent case a couple weeks ago, we saw where their concentration was around 30 or 33% that they were using. So the fluxer itself can be designed to have both of these concentrations applied automatically, depending on the design and what the requirements are for this process. The flux tanks are used to keep the flux in agitation and to keep it at the proper ratio. One of the issues with flux is it gets very hard if it settles, and it's very difficult to clean. You're basically going to have to take a chisel and hammer to clean off the flux where it begins to build and is allowed to harden. So part of the job of the fluxer is to keep the flux in constant agitation to prevent any kind of flux settling. Obviously, there's certain issues with the flux because it is very corrosive, done in a slurry, and it can come out in a mist. And if you spent much time in facilities that are doing a lot of wet spray fluxing, you can feel it on your skin, on your hands and things. So it does create a mist in many cases. That mist adheres to the outsides of the furnaces, to other equipment around the furnaces, to the building, the support columns in the building, things like that. So frequent washing and cleaning is very important when you're using your wet flux because it does build up and get very hard. So part of the design of the fluxer is incorporated to prevent flux buildup and to aid in easy cleaning. So now you have a clean part and it's fluxed. We're looking at the dry off oven at this point. So the dry off oven is going to eliminate all of the moisture, or specifically the oxygen from the core, including the internal parts of the tubes. So if we keep oxygen in the tubes, if we don't get that fully dry in the drying oven, and the heat exchanger carries liquid or water into the furnace, when that is heated, it will expand and the oxygen will contaminate our nitrogen atmosphere, very high levels of nitrogen atmosphere. Again, similar to the thermal degreaser, we're about 500 degrees Fahrenheit to dry the parts. And because of some of the complicated designs of the heat exchangers, directional airflow may be required instead of just heat alone. So in some cases, heat needs to be applied in certain areas to eliminate internal oxygen or internal water from being eliminated out of the tubes. In the profile that you can see, the temperature profile, it's heating up in the drying oven to about 250 degrees C. And then in some cases, we're losing a lot of that heat before we get into the furnace as we go into the curtain chambers. And there's some things that can be done to eliminate that dip that you see in the drying, between the drying and the furnace chamber. Here's another temperature profile. As you can see, the first steps, we are heating up to 250 degrees C in the drying oven. We're maintaining our heat, and then we are ramping up in the braze furnace. We get up to about 605 degrees, where the filler metal is melted for maybe 30 to 120 seconds, depending on the process. And then we very quickly cool that part down. You can see the two different levels. The first level, we're cooling in a nitrogen atmosphere, and then the final level, under cooling, we're cooling using the final air blast. But this is a very typical atmosphere profile or temperature profile for aluminum brazing. The plus or minus 3 degrees C at braze temperature is required. There can be some temperature variation during the heat up cycle, and that is acceptable as long as the parts all come together at brazing temperature within that temperature window. Obviously, the heating cycle should be as short as possible, one from a production standpoint and two from a utility standpoint. Heating rates up to about 50 degrees C. I think the last slide we saw was 45 degrees C, but those kind of heating rates are not uncommon. Generally, you're about a minute and a half, around a minute to 2 minutes at brazing temperature, which is enough to melt that liquid fillet to form your joint. The longer the filler metal is molten, the more severe filler metal erosion may occur. So just to put it in there for 5 minutes at temperature wouldn't be good either, because you're going to create a lot of problems as well. So it is a very short time. You get in, you get up to temperature as quickly as possible, go through your required time at braze temperature, and then cool down as quickly as possible. As far as the furnace requirements itself, we're looking at 600 to 605 C as a typical brazing temperature of the part. The uniformity across the entire part, including the tubes and headers and fins, must all be plus or minus 3 degrees C, generally at 2 to 3 minutes or less. The nitrogen atmosphere that required, incoming nitrogen, looking at negative 70 degrees dew point or better with 5 nines or 99.999 incoming purity. Historically, the nitrogen has been supplied via bulk silos that are at the facilities. In a lot of cases, more recently over the past several years, people are looking at generating their own nitrogen. Several years ago, it was hard to get that to those incoming purity levels, but the equipment now generating your own nitrogen is much better, And now we've seen several recent cases where generating your own, you can get the 5 nines incoming purity. As far as furnace atmosphere inside of the furnace for the process, the Nokalok handbook states that it must be below 100 parts per million of oxygen in the part. That will get you a successful braze. But in some applications, you're preferring to be at below 30 parts per million. And then when you're looking at like fluxless brazing, for example, you're looking at very, very low purities of oxygen in there, in some cases less than 10. So we are looking at a very clean, high purity atmosphere that will give you the lower the ppm of oxygen is, generally the better cosmetic or shinier appearance that your heat exchanger post braze can produce. Obviously, we've talked about before the fast cooling rates and sharp temperature profiles are advantages for good quality parts as well as lowering utilities. As far as the types of cab furnaces, there's many different types that are out there. We're going to look at batch here in the next slide or two. You have semi-continuous and then your continuous furnaces, and there's benefits and drawbacks for each one. Your batch furnaces and generally are a smaller footprint. You're going in and out of the same door. All the heating and coolings in a single chamber or minimized chambers versus some of the continuous processes may give you long cycles. It's not generally looked at as high production types, although with small parts, some of the sizing can produce fairly high production numbers. And a batch furnace does allow a high product mix as well. The ones we're looking at are using convection, where we're mixing up the atmosphere, which is allowing a high product mix for somebody who's running various different products at lower volumes. And probably as far as the cost per part, your batch furnace is going to be your highest manufacturing cost per part. Looking at a semi-continuous furnace, often they can look like your continuous furnace, but instead of the belt moving at a continuous fashion, it is indexed through multiple chambers. Like I mentioned, can look like the continuous furnace, but can produce very fast cycles, much higher production qualities, and allow a high product mix. And then the continuous furnaces, which most people are familiar with, can have multiple chambers for the different processes that we saw. Many doors, have the fastest cycle with the highest production and low product mix. A lot of these furnaces are running 24/7, 50 weeks a year. And in some cases, they're running the same parts or very few product mixes and very high quantities of each of those parts, where recipes may simply need to be changed, whether it's heat or speeds of the belts. And in the continuous line is producing the lowest manufacturing cost because it is a continuously moving belt that once it's stabilized, it's pretty easy to keep the atmosphere and temperature at a quality level. So looking at a batch furnace, this is the top view looking down. At the bottom is the belt or the roller, the material handling. So the part is loaded, or the tray full of parts is loaded. The part is then indexed over in front of the furnace. You can see some darker 3 lines there, which are chains that would pick up the tray, indexed into the first chamber you see with the 2 fans. That would act as a purge chamber where we're reducing the oxygen levels while that inner door is still shut. When the oxygen levels are appropriate, that inner door opens, the load then is transferred into the brazing chamber. That door shuts and we go through our heating cycle. As we hit braze temperature, we soak for 2 to 3 minutes, whatever the process calls for. Then that inner door opens back up and the part comes back out. Now, instead of acting as a purging chamber, that chamber is acting as a cooling chamber. So it is a multi-use chamber, which gives us a little smaller footprint. After the part is cool, it can come back out onto the material handling section of rollers and then can be transferred to the left. And you see just a final air blast where you're just utilizing your plant air to put a high volume of air through the load to cool the parts down for manual handling, fixture removal, any kind of testing or painting that may need to be done. The batch cab that we just saw, We do have a standard size of that specific equipment. Obviously, can be tailored to be designed to meet your exact sizing. But the standard that we have is 36 inch by 36 inch by 48 inches long, with a max load weight of around 450 pounds. So you can put as many of your parts in that area, which includes the product trays and fixtures. Keep it under that weight of 450 pounds. Would give us a total cycle time of around 30 to 90 minutes, depending on the load mass. Two-chamber design, where we're using the brazing chamber as one chamber, and then a combination purge chamber and cooling chamber, which allows us the smaller footprint. And in this case, we're using electrically heated bayonet elements, nickel chromium, in tubes and protection tubes to protect it from the atmosphere. At that 450 pound total, the design is calling for about 180 kW heating power. The standard utilities, nitrogen consumption would be about 1500 CFH at the purity levels that we spoke about, and then it is run on electricity and can be tailored to whatever your local requirements are. As far as the higher volume production, we're looking at the continuously moving belt, which are your continuous lines, which are generally running 24 hours a day, 5 or 7 days a week. Mass production, one product size in very large numbers. In some cases, they can be fully automated. You can have your operators loading them by hand, unloading them by hand, or loading by robots, unloading by robots. The continuous furnace allows a high brazing quality because you're in a continuous, repeatable fashion. You get a clean atmosphere, you get great temperature uniformity, sharp heating and cooling profiles, and it is a very repeatable process, which is very important, especially to some of the customers of the heat exchanger manufacturers. The continuous cab solution here, the radiation. There's a big difference between heating with convection versus heating with radiation. In radiation, we're heating the muffle, which then heats the internal parts in a static environment. There is no fan, no moving atmosphere in where the actual heat exchanger is. It does allow high volume of the same parts with excellent temperature uniformity and repeatability. And because there is no fan, it is the lowest cost generally overall when comparing radiation to convection. When we're looking at a cross view down the furnace, we can see the radiation muffle. Inside of that muffle is where the belt is pulling the parts through, where all the heating does. So the heating elements above and below the load are heating the muffle, which is then in turn heating the parts as they are moving through the furnace. I put in a couple pictures of a variety of different muffles. There are different size and shapes and corrugations that can be done depending on the size, length, width of muffles. But in generally, they're looking at stainless steel muffles, whether it's 304, 316, or 316L materials. But we do a lot of different muffles. You can see the one photo there. I think that was about a 98.5 inch muffle that we created here in the shop. So we do have a quite busy aftermarket area, also building new muffles for people, or different customers. So we do definitely put out a lot of muffles and have a lot of experience on various processes and designs from a design perspective and a welding perspective on these, because everything is going to be gas tight, welded and atmosphere tight in these furnaces. Looking at a convection versus the radiation, is you're using convection to move a high volume of atmosphere through the heat exchanger, allows a greater product mix. When you're running the radiation furnace, it's very repeatable. You're running the one part over and over and over again, but your convection is going to allow you to do a greater intermix of products just because of the nature of forced air and the ability of the part to maintain and accept the heat. And in some cases, you can add a convection preheat in front of the radiation and braze furnaces to shorten up the overall thermal cycle, add even a more greater product mix and flexibility from the furnace. But again, adding the fan and a different muffle design is a much higher cost than your radiation. furnace. So that is very quickly and very generally the steps or the furnace view of the aluminum brazing side. Uh, we do have many questions, and I see that there are some questions that came through during the webinar. What we'll do is we're going to get back to everybody who has submitted questions throughout, whether it was when you registered or throughout the presentation. We'll be back to you with some answers. But in the meantime, I would hope that some of you would consider to look at the 2025 Continuous Furnace Brazing Symposium in Niagara Falls of this year. There will be more details coming on our website and on our LinkedIn profile. And if you're not following us on LinkedIn, because that is a place where we are very active as far as upcoming events, please scan the QR code and follow us for the most updated information. So thank you very much for participating in the webinar today. I will be reaching out to several of you individually after this for some contacts and some of the comments you made. And we'll take what we've learned and what we've received from you, and we'll see what our next topic will be. Maybe it'll be very specific on certain parts of this process, but we'll review and we will come up with further webinars in 2025. So I appreciate very much your time, and I look forward to talking to you at a future time. Thank you.